Welcome to the Gyan course on codes for distributed storage. I am Adrish Banerjee and it's my pleasure to have Professor Udaya Parampalli and Professor Aaron Harwood. I'll first introduce Professor Udaya Parampalli. So Professor Udaya Parampalli did his PhD from IIT Kanpur and he's currently Associate Professor in the School of Information Systems and Computing at University of Melbourne, Australia. His research interests are in cryptography, sequence design, and coding theory. So, first few lectures are going to be given by Udaya. Then, when Aaron's turn comes, I'll introduce him.
Okay.
Udaya.
Thank you, Adrish. So, this idea for this course came up when I was visiting last time IIT Kanpur, and Adrish is an expert in coding theory, and I had a project was actually applying coding theory to actually practice, which is the storage problem here. As you can see that there is a lot of new results have come in this area from coding theory perspective on this topic, but in so far realizing such thing into actually practice and coming up with bigger systems on that, there is still a lot of research happening, and so our approach, we want to kind of use this idea and to understand the tasks here in this new field. So the outline, I would like to come up with a context of a large scale storage and a brief introduction to modern storage codes, and I'll look at this from mainly the motivation part, what is there, and erasure codes. And if you look at the history, erasure codes have been used in storage since days of RAID, and it is probably 90s. There were lots already been used, and lots of Reed Solomon codes. Some of the things were used as well. So what's new? Why it's came up new this, and that's really the focus of the practical context in which these are come. And in the age of new cloud, everything is now moving towards cloud. So I will focus on some important class of ideas that came under this context. So that will just motivate into this area, and then I will briefly explain what is our approach in this area of research, and whatever little we have done in this area, we would like to consider that. And I'll also give a brief course organization in this talk. So the main idea is when you have a large scale distributed storage system, why do we need a large scale distributed storage? That question has come, and this is when the application context comes into picture. For example, many internet driven applications such as social networks, file and video sharing, these kind of applications are constantly growing, and those companies are whoever who is providing these services, they can't keep all this data at one place, and they have to distribute across the geographical boundaries. And so the distributed thing is a kind of a necessity, and it's not something kind of a design choice. It's because the whole world is distributed, and also then everybody requires to have a seamless access to the reliable storage, and that's the context in it. And the simplest how they are implemented, basically what they do is, if you have a file that needs to be stored, and you basically divide them and put across the different storage areas around the world, and these things are kind of realized in practice by using a large scale data centers that may be built at a place, for example, that the electricity is easily available and so forth, but then you have to come up with the networking infrastructure, delivering them to the users wherever they are. So in doing so, so generally these are built on traditionally by using some commodity hardware, so you don't really special things, so you buy cheaply hardware and put together. and these commodity hardware often fail. So it's, I mean, people have done some experiments and have looked at it, and so all these storage devices are there, and you can, as time progresses, and watch how many will be active. And so there will be, at any point of time you take, there will be some nodes that are always down. So if data is spread across these areas in these nodes, obviously when it is required for computing or even access, that is not available. So this is another thing, is the data is stored somewhere, but then what is the use of that data? That data either is that sometimes you may have some computing programs running on them, so that means that for those computing processes, wherever they are, that they are also computers spread across, that data should be available. That is one type of thing. And these computing devices could be even end devices that the customers are using, maybe their mobile phones, etc. So it could be, so it could be many places. You see the point? And so first of all, the availability of data for the processes running in the distributed system, as well as sometimes people may just want to have the access data, that also. So access and accessing for the storage, accessing for the computing, this is also important. So you can see that what we are looking for is not just, for example, when the coding theory initially was used, the main idea was there is a source, a sender is sending some information, receiver who will consume it, and it's only the channel that will pose some problems to these signals, and the purpose of coding theory is to somehow recover from these channel errors and deliver it to the receiver. So this is a very nice simple model that we could understand. The coding theory grew up with this. Now what does the coding theory has to do with the storage here? It's the same kind of issue. So when in the next talk, when I mention, I will also mention about this kind of models. So to come back on it, I will just dwell on the context a little bit more thing again. Is the main idea is that the devices are to be stored and they are often fail, then there needs to be some kind of a reliability. And so coding for reliability, that is also not new, this is also there. So for example, in RAID, erasure codes were used, so you could do some other additional storage which is based on the main data, and in case of some nodes fail, you could recover from those data. But how it is adopted, for example, here some data is there. For reliability, simplest one is to use replicate. Replication is the simplest technology that's used. So these are, in some sense, I was just talking about the same things. In case storage devices are now made from inexpensive commodity hardware, they are always susceptible to errors, because the errors could be either they are not available, or sometimes some processor have sent out some request for the data is not available. So it's also sometimes called as misreads. Okay. So and some of these also, and there are many other things could happen, which is basically this one I'm creating the third point quite wide open. That could be temporarily some available, maybe because of engineering and technical issues, when those who are doing so, nodes themselves is not available, but it might come available after some time. So during the time when it is required, what has to be done, those are the issues we need to look at it in the storage setting. And also the main main idea is this, the cloud computing techniques. Now they look at this everything as a system. So the storage system also works, and so it requests, for example, some job is required and there is a system call made out, and if the data is available, further actions could be taken place. So this is how the distributed system works. So this kind of some data is not available either because of the busy, sometimes the node is working, but it may just not be available at this point of time. So how do you handle such things? And one of the simplest strategies is known as replication as a strategy, and many distributed systems when came up initially to support this, they adopt easily, because the replication is the simplest way of coding. In fact, in the coding theory part, when we will show that the repetition code itself, it's actually a very optimal code. You couldn't do better than in some sense. It's a trivial, we'll say, for the coding point, but they can be used. So how it works in that case is a data pertaining to a file now split up into multiple chunks and they dispersed across large connected network. With the replication, what happens is that every piece of data, wherever that is available, it's also available at maybe another place in a duplication strategy. In a triplication strategy, it will be available in 2 other places. So when you organize a distributed system, there will be always some special nodes which can control the activities of the other nodes, and sometimes it's called as name node in Hadoop. We'll come back in other cases a master, and there other could be slave nodes. But this idea that wherever it's replicated is as kind of a part of the metadata that will be available. And then what happens is that when you program with such a paradigm and the programs are already coded and spread out, if particular node is not available, it can say, okay, go and take from the other node and get back the data. So those are the part of the things which the distributed systems will do. And we haven't talked about this, old coding theorists or the codes over storage is not that, they want to go away from replication because replication is very expensive. So for every data you go replicate by 3 times, it's a pretty expensive thing. So you would like to kind of reduce, and can we come up with a non-trivial interesting coding where you gain advantage over it. Now for that, but still, for example, this replication in even modern system is very popular for hot data. So again, I should define you what is hot data. It could vary. So in any distributed system, if some storage, some functions have been designed, and that data is used constantly for making computations, then it is alive. It's a hot data. For example, it could be, for example, Facebook users, who has logged in, and there will be some active things happening. So Facebook system can understand who may access some of these data again. So in order to serve its users properly, its computing will be organized in such a way that those data is always ready to be fetched, either at the end devices or in the middle devices. It's the whole system in the network. And in such case of hot data, you don't want to waste time in for example, a node fails to recover. So basically, I won't come up with a recovery yet, but just talking about the replication. So popular, that's what hot data is. Still the replication is a popular one. But what happens is after some time the job gets done, and let us say the distributed system thinks that this data is enough, now we can store it back. At that time it becomes cold data, and the normal practice is to RAID it and put it back. So for example, you don't keep all the 2 copies replication, you only copy the main files and some parities that is required in case some nodes fail. So it will be compactly cold RAIDed. And so initially some of these ideas in coding theory came up for the cold data, and we are moving on to this. Now how does erasure code come? Erasure code is a cost effective solution over replications. That's been there already. So now I will throw some ideas from coding theory, how for example we can understand. So in coding theory, k symbol of information is encoded along with n minus k symbols of parity to make the whole length nk. So normally that's how the general definition of, I'm making a very vague definitions for the coding theory at the time. I don't even specify what these symbols are from, which finite field, which things, but it's just k symbols, and add some extra parities. And some of the coding parameters probably everybody should be aware of is, for example, length of the code. N is the length of the code. Now k becomes the number of symbols. And obviously this code is defined over certain distance matrices. For example, one of the simplest distance metrics we do is the Hamming metric, because if a code is represented with some data, if there is an error, it will change from one symbol to another symbol, and one way of actually distinguishing there is some error is to have some idea of a distance. So this was the original symbol, this was the next symbol, what's the difference between that? And somehow when we correct, we would like to kind of get a code word which is closer to that. and that is all these comes up with a lot of engineering and the actual practical assumptions that happen with the coding theory, but we will also give some attention into this aspect in the first part of the course, so that we can understand the issues very clearly. And the next thing that I would like to mention in why the erasure code. What happens with the erasure code is, so as I told you, the positions of the code word means there is the information, k bit of information and the n minus k bit of parity. When something goes wrong, that the system will know exactly which one has gone through. So in case of erasure, you know which symbol is in error. Whereas in case of error could happen anywhere, and the purpose of the code is to recover that error. So that way handling error is much complex than handling erasure. So erasure, you know exactly where the kind of thing, and all the erasures are actually done because we want to actually maximize, and they are called maximum distance separable codes. And also another question, depending on the background, we would like to understand what is this maximum distance separable. So when we define some codes over this, the codes, this is some kind of an optimality that you couldn't get much better distance properties other than what we have. So it's got a maximum. So all the code words are separated in a space, and that's actually the maximum possible. You couldn't go much higher. So that with that actually what this also helps you, what happens is recoverability is also gives you an idea of recoverability, because when there are n symbols are there, any k symbols is sufficient to obtain the data, and this is also called as k out of n property. So some of these concepts came up in last centuries, and who has learned this from scratch with very from fundamental principles will be lucky, because that is very interesting in its own sense. So they were applied for Shamir secret sharing schemes. It's the same idea that comes. Reed-Solomon codes that was common in the coding theory context, and these were actually made a lot of influence in the way the last century communication and computing era. So this is the examples for the Reed-Solomon codes, and we will also look at closely these objects. What are these? Are Reed-Solomon codes in the things. So from, let us say, again another question will come, what is erasure code? You can go around, computing people will say, oh, this is just a data protection technology. So people can come up with a lot of definition based on how they use these ideas. So whereas to a coding theory person, erasure code is more towards from explaining in k out of n property and these kind of fundamental things. So whereas the person who says it is erasure coding, he will just think that, oh, some disk is not working, I'm going to actually recover this disk by talking to any other k other disk because of these kind of things. So this is how you do, and we also would like to understand. And so how are they defined? So the Reed-Solomon codes are the very popular objects. They are defined over a finite field. So here the Reed-Solomon codes, I already mentioned informally the property. So what does it means is that given any integer, so integers means it has to be now positive integers greater than 1. So you could make some of these definitions as precisely as possible if you learn this coding theory from scratch. So this is one of the advantages of learning some theory from scratch, because then you can understand everything very clearly. But I'm making it some kind of vague definitions, but again also kind of throwing in some new terminologies that comes from those finite fields. So finite field is just like a real number, complex number, but except that the alphabet size is finite, whereas in real number the alphabet size is infinite. So that means what's the properties that you ascribe for real numbers and complex numbers applicable to finite fields as well, except that in the finite field they're all finite. So the finiteness actually is an advantageous, in some kind of a boon, or also some kind of a bane, in the sense that it does, for example, if you don't define it properly, it cannot be used in day-to-day like things. Like if two numbers, two lengths you add in the real number, you can anticipate how it will become bigger. So maybe you can take 2 sticks and add it, it will become a bigger, and you can have a real life analogy with it. But in case of finite field, if you add 2 finite field, it will give you objectives of same size with the same thing and no such real information. But if you could map it properly using Hamming distance and others, making very interesting things can happen. So these Reed-Solomon codes are generally defined as a k-dimensional subspace of n-dimensional vectors. Now again, just throwing these words, and at this point don't get confused, they are not difficult thing to do. So one way to kind of is a k-dimensional subspace is you think of a situation, for example. So I'll just go through, if you have a length n of any bits with say n length bits, okay. It could be over real numbers, it's not a problem, it's a length n length vectors. In a computer science it will be an array of length n, and you want to consider all possible vectors coming out of that. And for that you don't really worry about finding which one I should use as a basis. Now one of the simplest bases you can think of is 1 followed by 0, next one is 0 1 followed by zeros, then 0 0 1 followed by 0. So you could have precisely n different vectors which has a specific value of 1 only in an ith position, and then any vector of length n can be represented as a linear sum of these basis vectors. This you could follow, right? Like how do you construct for example an array? Yeah, same idea. When it is defined over a finite field, that will be acts as a vector space by understanding underlying the group properties. Then what we want to do is that, but let's say if you take a k-dimensional space, it's actually much smaller dimensional, but we want to now add some extra redundancies and stretch these k-dimensional vectors to n minus vector, so that now we will hit this all k-dimensional vectors under a bigger dimension. And so that idea will come under that's why Reed-Solomon code can be defined in this specific way. Then RS codes, they have actually maximum distance property we could see, and once we start with some fundamental axioms, and then you could easily familiarize yourself, oh, this couldn't be other than this. So that is a kind of a proof. So you start with some proof is basically an idea. You start with basic axioms, then you make some deductions applying these basic axioms one over the other and seeing a new result, and you can't be, that's all it is. So RS codes has some canonical forms, as I already mentioned. So it has a first k symbols as a information bit and n minus k parities. Now I mean, before basically I want to give a general overview of these things, and what is the error correcting code in network setting. So if you will actually open up any network coding book, the error correcting codes are actually shown in the link layer, in the first layer itself, because that is when two nodes are sending some frames across each other, and the other device needs to make sure that whatever the frame that it has received is intact, is correct. Now you could actually, if you know the properties of that particular link, the channel, you could also add error correcting code. So you could take k information and add some n minus k information so that to recover from errors. But if you ask any network engineer, would tell you nobody would use at the link layer any error correcting codes. What they do is they only use some kind of error detecting codes. So for example, by chance if some errors have happened, I should have some kind of a code to check whether that's what is used. CRC checksum is used. It's a small checksum to use, which is like finding like a parity. Yeah? It's also a coding idea, and that is used, and that's what the information in data units in networks. That's how it is used. But obviously, when the networks, this was when, for example, when the network were constructed using modular form. And we have a TCP/IP networking to connect everything. This is a part of the standard. But as and when we have more and more networking applications are coming, so where you really use the non-trivial error correcting code, that actually happens in network layer. So what happens is that in the network layer basically is a much higher layer in the networking concept. And so for example, you may be receiving a content distribution thing, maybe a video from a server, and that time if you for example all the information that you require will be put inside the IP packets will be sent to you, and if some packets miss, for example for some other reason, then there is already a mechanism available in the networking where, for example, TCP/IP, it will request them to resend it, and that would delay the process, and the servers wouldn't like to have it. And so one could come up with an application that runs above this network where in case of some packets are lost, you could actually recover from parity packets. So you have a information packet, k bit of information, so where the first bit of let us say all this k information can be related to the first bit from the other parity packet. So instead of actually coding via horizontally, you coding via vertically. So this distinction of coding vertically horizontally becomes very important. So what it means that you could have an array of extra packets. So this will reduce and there were lots of happens in fire codes, fountain codes, lots of improvements thing, and that's not the goal of this course. So I'm just telling you about there are other things where coding is used. What we do is in the storage course, what we do is the nodes are distributed and connected by a network, and so again in this to more formally each file is now divided into k data blocks of fixed size, and m coding blocks, which is n minus k will be coding blocks, and it will be stored. So once you define whatever code for a one symbol, we can extend the same idea to however big the file may be. So you could define this idea k or n using say maybe a byte, but rest of the information can be defined one over the other. So do you see the point? So one code can be extended to handle much bigger. So really we don't need, just because we have a 1 gigabit of data, we don't need a code of 1 gigabit length. So you could tell the code length actually depends on the number of nodes we have in the storage. So how does the file reconstruction work? So for example, if the k by m storage devices are there and some nodes are failed, and what you do is that you decode those ones, you could recreate those last bit by using the information available in the parity nodes. So this is how, but this is already there. So what is the big issue now? So erasure codes were employed in storage devices in the early days of disk technology, and what's new? So this is a fair question, you can say. So what's happening is at the moment now, see this is about actually the amount of data, the data explosion that's happening now. Now think, for example, coming here, I just checked a thing, how many smartphones are used in India at the moment currently? Do you have an idea? It's about 500 million. 500 million smartphones only in India. And so if you assume that the rest of the other people also, like India is a very big country, so it's let's say about 1 billion smartphones are already, and each smartphone, let us say, will have for example 1 MB of a photo every day. Then if you do it for, let us say, for 1 year, that will be approximately another 365 times 1 MB, roughly say 1 gigabytes of memory, and there are about, and if you consider for all the smartphones, is already about 10 to the power of 17 bytes. So all these things are, I'm giving actually a very best case scenario. So then in some cases it will be much more, and all this may be stored and others. So this amount of data generation and its usage and subsequent storage for archival and other utility purposes. So for example, some data is stored, it doesn't mean that it's not just is only kept it for a storage. It may be needed for some other application, and that particular computing, that application might generate some more data and as a part of things. So you see, this way of data generation is growing, and that is what the main problem faced by some of these big companies like Facebook, Yahoo and Google, they now store lots of these images and videos for consumer worldwide. So data centers also, because of this, what's happening is now the data centers are also they are using power, and at the moment now they really started to be filled. I mean, they consume really almost 3% of the world electricity. So anything that is you minimize this, you will be doing a lot of help to the earth, because we will be reducing the power for consumption. So the issue is that data is inherently distributed, and all these were sometimes constructed using commodity hardware, and they often fail, and so the recovery now involves the multiple issues. So main idea is that when you are recovering, already now this data is spread across. One way to do that, whatever the parity information that is kept for these data need to be fetched from different parts. So one of the resource that you need is bandwidth. Okay, this is the first thing. Whereas in the early days of RAID, the devices were probably as a part of the commodity hardware, probably within the same cluster, and so the contacting a neighboring thing was not a big problem. But now the bandwidth is a big issue. And also, while connecting this, you will read the disk read, so you will send out a disk read. So disk read and amount of disk read required to repair or recover, that also is another source. And then over and above, the software that uses them is a distributed software, and how it behaves, like the complexities of that constructing such distributed software, that also affects this. So this has the recovery now involves this, and this recovery has come into the main focus of things, and that is when in the early days in 2002 and all, when Facebook had these big clusters, they come up with this called HDFS RAID, basically that uses 1410. I'm just telling you, we'll probably understand a bit more clearly about the parameters of these codes and how they are used once we go through a bit more computing. The Reed-Solomon code was adopted for storing cold data in Facebook storage nodes, and this is also used in Hadoop distributed file storage. More information you can type. The idea is very simple. Is you have 10 nodes that's called information nodes, and there are 4 parity nodes. So you can see that the code is just a length 14 length code, and at the moment I haven't even specified how they are used. You could even think like a binary bit, but in this case it's a 14-son Reed-Solomon code over, say it works with either 8 bits or 16 bit or 32 bit. They wouldn't go for other type of finite fields that we're going to study, but that's because that's easier to operate. A byte is a word and so forth. So normally in the initial it's over byte, and what happens is that if you may have a say 64 MB of data, which is a one block in the HDFS, that 64 MB, the first all the 10 blocks will be set into 10 different nodes, and again the parity, there will be similar data, blocks of data will be generated based on that. So for example in the 11th node, the byte is simply say exclusive or sum of all other ones. So first byte in all these blocks will be related to these parity nodes, first bytes of these parity nodes through the Reed-Solomon equation. Then once you have one such equation, you can run through as many like you can. That's the kind of system that exists right now. Now let's look at this. Was the thing, this was for the cold data they developed, because let us say if there is any hot data working, then they'd use replication. So the HDFS use replication for hot data. That means whatever the blocks of data is there, that will be available in 3 different nodes, and any program that you write on this would involve understand this one. But once the data is finished, then all this data node, all the replications will be removed one by one slowly, and then we'll put 4 extra parities and store. And then in future you need any data, the system can go back and fetch them automatically. So what happens when I repair things? So this is the idea of a repair. That is where the new storage code's motivation comes from. So the repair is basically, so let's say some node has been gone. In this case, one of them will go. And so for example 1, and I want to, 1 is gone, and by using any other 10 nodes you can recover it. Okay. So obviously with the Reed-Solomon code, all the parity nodes depend on all of them, so you need at least that many nodes. So if I want to create one 64 MB of data, then I need to really download 10 times 64 MB of data and recreate it, because the whole process is like a sequential. I create one byte by byte and then store a new byte, and that's very, this requires network bandwidth, and also the individual these data nodes also has to make those reads, and it has to send it, in some form and send it. So a lot of activity happening just for repair. Now you see, this is very inefficient. Can we do better? So how can you efficiently handle this node? So as I already mentioned, RIDE uses a simple idea of a stripes and blocks. So the blocks is the one which the data is organized as a single node. The stripes basically tells you the connection with the code. The stripe is one stripe that all the bytes are related. That's called the stripe. And the code word now represents, so each code word now you can think it as a stripe, and blocks of data can be arranged in different nodes. So NK now can be already expanded to a long file. A block in parity nodes are functions of blocks of information nodes. Now let's take an example. Now we want to do it by efficiently doing MDS code in some idea. So so when you have a code like this, I mean here I have thrown, and I will make sure about the actual meanings about some of these things a bit later in the regenerating code. But if you use some 4.2 MDS code and assume that we have any 2 nodes will be sufficient to recover data in case of a node. This is an example. And so basically when some node fail, I mean how many blocks do you need to download and repair the failed node? For example, A1, A2 is failed. And I want to, I mean don't worry about it how this code is constructed, because I'll go back, and when we understand a bit more on that we'll go later. But assume that now all these things here, as you can see that you will see the 2 bytes every time, so you may have some questions on it. But assume that so when you have such four nodes are there, and any one let us say the first node is failed, how many blocks do you need to download a repaired node? Definitely, because of the k out of 2 out of 4 property of a Reed-Solomon code, you contact any 2 of the surviving node, you can recover it. Correct? Is that clear? So for example, you can choose one of the A1, B2 and A1 plus B1, A2 plus B2. You can use these 4 things can be downloaded and do. That's what the Reed-Solomon code example that I mentioned in this one. So depending on any failed node, you need to contact any other k node, and same way here I need any 2 of them. But that requires how many blocks do you need? 4 blocks. Can you do better? That's the idea that came up in a kind of thing. So for example here, so now one node has been deleted and you want to really recreate it, and can you do how many blocks of do you need to download? So you can see that now I can ask the first node, for example A1 by using these 2. So for example I can ask the second node to this one give you A2 plus B2, A2 plus B2 that was there, and this one A1 plus A2 plus B2, and ask you B2. So I'm dividing, instead of dividing the entire block, I only divide half of the information from other blocks. So I divide only half of the information here. So half a block, half a block, half a block. And now I can actually, for example, since I know A1 plus A2 plus B2, I can exclusive OR and get this separately. and similarly I can use B2 to get back A2. So basically I can say 2 nodes are enough to recreate, but 3 blocks are sufficient, and happen to be that. Can you come up with some idea where how many really the sub blocks I need to really recover? But in this particular case you can prove that maybe 3 is necessary, you can't do less than 3, 3 is necessary, so 4 is sufficient, 3 is necessary. Okay. So ideas around this one came up as regenerative code. So, but you also have a repairing, for example, the idea that I explained works well for the repairing an information node which has the information, but if you are repairing a parity node, then you have to do a bit more information. So maybe some of these nodes have to do a little bit inner computations, because in this case remember A2 B2 he can easily send. Then this node actually can send as a linear sum of what is available, and that will be used to repair this node. For example, here A2 B2 this one, and the next one this one, basically instead of sending A1, so he has only B1 and B2, but he will send some function of it B1 plus B2 to send back here. So the idea is that main idea is I want to recover the particular symbols, and I need to ask you the nodes to send appropriate functions so that I can align and get back whatever I want. So this is also kind of an interference alignment. This idea came up in mobile computing literature for that's where people wanted to actually have a high throughput system through that, and that got applied to this, and these are some new ideas that they came. I want to actually fully explained actually how the calculations happen, etc., but at least you get a feeling that it is possible. For example, I don't need to really use full erasure code, I can come up with some interesting codes to reduce the bandwidth. Okay. So so in fact the node reconstruction now is influenced by the 2 types of network resources. One is basically the bandwidth, other is based by the discretes, because you need to get the more number of nodes, like actually discretes are the number of nodes read. So these 2 issues have influenced development of new codes in this area. One is called category called regenerative codes, and the second one is called codes with locality. So in the regenerative codes it comes up with the codes with the property that I mentioned in that example, where the individual nodes can send some information in a way that helps to reconstruct it in a more efficient manner. And the second one is codes with locality, where the nodes, when certain things go down, you actually contact minimum number of nodes to repair a particular node without really going into the structure of the entire node. 2 important distinct ideas in the storage that came up that initially I mentioned about regenerative codes. This was a paper by Dimakis and other people came up with, and it also got the best paper award and others. And also another one is a codes with locality. This also kind of very influential thing. So we want to, this kind of papers has lots of interesting ideas, and that requires the further new ideas in coding and finite fields. So the model for codes for regeneration, how does it work is there are k nodes, and there are about the rest are other parities. The nodes have been spread. So when in case of a reconstruction, still a k out of n property would work. But if you are a repair node, what the repair would do is it will actually extract some fraction of symbols from these nodes, and so that is represented by beta here, and it contacts d number of nodes, where d is now is greater than k but less than or equal to n minus 1, because if a node has failed you can only contact n minus 1 of them. So within that you have an option to go to d for that one, and it can generate a part of data. And you may even think of having, say for example, maybe there is a code that exists beta 1 from one node, beta 2 from the other, so you can also do it, but you can also you can easily conceive that the best option would be to have a equal number of things for it. You could, those are the proofs that comes with that, and once you have that, what the authors they did was basically by using some network coding theory, they would show us about the relationship between the code parameters and the file size. So in order to, so there was an because of this framework, now the design have an idea. You could use some alpha different symbols per node, and you could use and in case of a failure you could contact d of them, and each one fetching beta from there, and so now d times beta is the bandwidth that is required, and k times alpha is the size of the file that is used. So in doing so, that can we now, what can we do better, in the sense that can we minimize the bandwidth, and also with how much you want to store in each node. And what it turns out that if you can't do both. So there is a trade-off between the amount of, so you can sometimes you can choose more number of symbols per node, and hence then you can gain a bandwidth, or you can use a minimum number per node, but then you can still minimize the number of the bandwidth required to do it. So this actually comes up with using a cut set bound. So he uses an idea called information flow graph. So initially the source nodes are there. These source nodes help you to get some code set up with k nodes having data, with n minus k nodes having parities, which is a function of each other. And then when a node fails, what happens is then a new node has to collect information from the existing nodes, and then repair it. So at any point of time with this regenerative code model, with the information you can come up with the information flow graph as the system develops from the state. From the initially start with the k node, but let us say some node has failed and then you recreate it, another node has failed, you recreate it, and this infinite flow graph goes in infinite way. And then if at all you want to actually repair a particular, get a node, then you need to, that node should have a sufficient information to generate that node. So, and you can actually get that bound by having a cut set bound in number theory. I will explain that in the later. That actually tells you about the maximum size that you can you can store in such a node, and that comes out with a bandwidth and storage trade-off. So, for example, in this one, all these are optimal points available. So, if you want to minimize the bandwidth required to repair a node, and that will be then you will have to spread a more number of information to that. So this will become an MBR point, and there are some which called MSR point, where there is a minimum storage points, but then you know that requires storage is minimized, but you might need to actually repair bandwidth there, and the main idea is to actually come up with somewhere where this is minimum. So this they establish it, and this is the main result that come, and sometimes you can have different optimal points. The optimal points could be vary from that. In the MSR point, you first minimize alpha and then you minimize beta, you get some parameters. And MBR point, you first minimize beta, that is the how much you how much you will collect from each node and to create, and then you minimize alpha. So these 2 points we will go through that. This is one of the flavor for the regenerative code thing comes. The other one is called codes with locality, and this was used in case of Azure. So the main idea here also in this case is that, let's say in the same with a we have a 1612 read Solomon code, where the sub symbols in the read Solomon code itself is another read Solomon code. So like first 7 symbols form another read Solomon code. So the parity here will be generated on that, and the next 6 will have another parity. So in case, say for example, one of the nodes fail, then the failed node has to only contact the nodes in that group to do that. So this idea actually they used, and this is in fact helping a lot. Now the question is in this case that you are adding some more parities to locally things, but whether we can still get a minimum distance bound, etc. And there's a lot of interesting ideas that come with codes with locality, and these people came. But on the other hand, the lots of in the space where these how these codes are used in actual practice, there were lots of new innovations came up, and some of the 3 papers that I mentioned here actually uses the basic RS code, but makes some innovations in the way the repair happens. And the other one is the tail F2 erasure codes that actually still retains the flavor of the earlier erasure codes, and come up with an erasure code that has a much larger erasure correcting capability. And then once the data becomes cold, this is a kind of adaptive code. So when data is hard, it uses more number of parities, and so hence it could be repaired quickly, but once the data becomes cold, it removes all the extra parities to make a small one. So that's comes under that. Then the other type of flavor for the codes come up with because 14.6 1410 Reed Solomon code that is used in Facebook, they're not going to so easily change it just because there are some new codes are there, and so people come up with another way of actually coming up with framework where you work with sub packets, and this is called sub packetization, and the Rashmi and other group in Berkeley, they come up with a new framework of piggybacking, which is they call it as a hitchhiker's guide. So what's happening is with the same Reed Solomon code, you divide the block into some sub blocks, and you intentionally add the functions from the previous block. So like some kind of a hitchhiker, when something is already running in a and you take a help of the previous person to move on to the next, and with that idea they come up with and showed an improvement of 45%, 45 to 50% improvement in bandwidth and etc. And some innovations come from practically significant papers. So there are some good source of interesting theoretical problems. So there is a distributed storage wiki, has a lot of open problems, and it's been there, and so if you are interested in theoretical space, watch this space. There are lots of things in the modern there. So then with this idea is that the sub-packetization is the main idea that I quickly mentioned in a simple example. So it is that we are able to divide the whole packets into sub-packets and use that to do the things. How much you can do, what is the range of sub-packetization, and these are some of the interesting theories they do. And most of the earlier ideas were done only for low rate codes, and actually coming up with high rate code. This means, so when it's a storage application, you're not going to actually have low rate means the k is less than equal to n by 2. So that means, but you would like to use less number of parity bits to do it. In that case, it is a high rate code. Coming up with high rate code is an interesting thing. There are some ideas with a framework to maybe when the code is already there, you want to actually get an optimum access property. So that's an idea. That means if a node is down and I want to get not only the minimum storage and also I want to get the optimum access. That means the amount of number of nodes that I contact to repair should also be minimal. And also there is some optimal update property. These things are also are of interest, and we have some results in that which makes which is a generalization of the few other papers that I'll come back and mention that. And you can also, for example, use it in because the thing is a security application, and most of the papers that deal with security application now assume that these nodes, some adversary can actually watch the node, but he will not get the whole node. So for example, when you have in a network situation, there are n nodes are thrown in the network, and the adversary may capture some fraction of that. He may not be able to control everything. So in the fraction, one of the simplest model is he's a passive eavesdropper. He just looks at what's happening in that node. So whenever that node is being used for some other application, he can just watch and do that. The other one is active adversary. Whatever he do when the node is there, he actively changes the contents of it. So how do you now actually avoid this, and so you can characterize in the information theoretic way to the these codes. What's our approach? So we looked at some initial results, like Sorbas or even piggybacking framework were developed with study based on large scale data structures like in Facebook. We don't have access to such there, because in that case the structure will be there at one place, and any meaningful research you want to do it on that, you need to access to real cluster. We don't have that one. And also we wanted to also study the effects of codes on systems on a general cloud, and for us we had an advantage of having Nectar, which is a national e-health cloud infrastructure in Australia, so we could make use of that. It's like a like Amazon, it's a research cloud, and so we can try the codes with this one. So we initially, when we realized that not all code discovered through can be applied directly because of the issues in this case, here they're not real the cluster, they're all virtual clusters, and sometimes some nodes can be geographically located. So really the factors that influence, which is same as the bandwidth, the RED, and also the number of nodes used, but the way it affects the computer, affects the distributed system is much more different. And so to understand that one, so we need to we actually use this, and we'll describe some of our experience in that course. So with this one, what I'm saying, we want to understand at least the nomenclature, information, whatever the definitions very clearly, but then our goal is to actually use the practical codes in that, and so like how we can use it in a practical context. And one of the things that we use is a MXR code, which only uses the exclusive OR as a thing. So because that way the node reconstruction can be done easily. So the goals of the course is that you first, as you know, only 30% of the people know from finite fields. So from information theory, so we'll first learn some basic principles in a much neater way in the beginning, understand what is finite field, what is vector space, and how do you generate some codes, and then study the Reed-Solomon codes and understand that Reed-Solomon codes has a perfect MDS property. How do the Reed-Solomon codes are used, and then we will introduce actually the modern innovations of this regenerative codes and codes with locality. And each of these idea comes up with lots of backgrounds and other steps, and some of the open problems are still they are there, and a lot of interesting things from the theory point of view. So, but on the other hand, to appreciate this and why that is important, we also need to understand the basics of distributed systems, how, for example, memory is managed, how these things, because that will be the future thing. So we'll also study some basics of distributed system, and Aaron will identify some of those things in that. So, and also we want to study with a well-engineered software like Hadoop, which has been done with a great care, and so there we could actually make some changes around that storage setting, and we looked at a geographical storage property. So because there are many applications there, inherently you can't put everything into a data center. There are some things where it needs to be inherently geographic. So that the reliability that gets from that, because you may, for example, you have a data center running at one point, if that data center is down, all your data is gone. But with geographically distributed clusters, if one of the geography fails, we could easily configure in another area. So what are the issues, what is how the codes work, and our research, our thing will be in that direction. That's what we go into the goals, of course. And we have got kind of divided into part. The first one we'll use some erasure codes and coding theory part. Then we'll show some advanced coding theory topics. Then we'll interlace with some distributed system concepts and then we'll look at the Hadoop one. So Hadoop system using Nectar, permitting how the networks work, we'll be able to show those, and there will be some guest lectures, and also Adrish will also give, the host will also give some talks in this. Okay, thanks for it.